Welcome, and thank you for joining us for this afternoon when we have the Division of Physical Sciences ongoing Science of Our Lives webinar series. Today, our focus is on understanding challenges to our environment and will feature faculty from both the departments of Atmospheric and Oceanic Sciences, as well as the Department of Earth, Planetary, and Space Sciences. My name is Miguel Garcia Garibay. I am the Dean of the Division of Physical Sciences, and it is my pleasure to welcome you to a very compelling and very timely series of presentations. In my role as Dean of Physical Sciences, I have the privilege of working very closely with scientists and students in the entire Division of Physical Sciences. In fact, Physical Sciences is a division rich with education and research excellence, which has had an enormous impact in the world through its 6 departments. In addition to Atmospheric and Oceanic Sciences and Earth, Space, and Planetary Sciences, we also have the departments of Chemistry and Biochemistry, Mathematics, Statistics, as well as Physics and Astronomy. We also have 5 interdisciplinary institutes and several centers. One of them, the Institute of the Environment and Sustainability. Well, today you will hear from faculty in our Department of Atmospheric and Oceanic Sciences who are working hard to understand the most critical systems on Earth, right behind me, and the impact that humans can have on nature. They are also working to understand how weather in outer space can have a profound impact on our planet. You will also hear from faculty in our Department of Earth, Planetary, and Space Sciences who are exploring Earth's deep secrets to help us grasp the way our planet works. To get things going, it is my pleasure to introduce our first speaker, Professor Lingsheng Meng, holder of the Leon and John V. Sinopov Chair in Physics and Geophysics in the Department of EPSS. Lingsheng will talk about earthquake hazards in California and measures that we can take before, during, and after the next big one. Lingsheng, the floor is yours.
Good afternoon, everyone. Thank you, Miguel, for this nice introduction. So today I would like to take this opportunity and talk about the next big one, which is referred to incoming big earthquakes on the San Andreas Fault. So if we look at, this is the earthquake distribution in US, we can see most of these seismicity or locations for earthquakes are on the West Coast. Now, to understand that, we have to look at the past history of plate tectonics in North America. So what you're seeing here is a plate reconstruction of the Pacific plate versus North America plate in the last 40 million years. So it's characterized by parts of the Pacific plate goes under the North America plate, and their motion transforms from a convergence motion into a side sliding motion. And that gives rise to the San Andreas Fault we see in California, and also subduction zones in Oregon and Washington states, and also the open up of the Baja California Peninsula. Now, the big player here for California is the San Andreas Fault, which hosts the largest earthquake in the state. So here is showing the fault traces of the San Andreas Fault. So luckily for us, not every segment along the fault are seismogenic, right? So these blue ones are the faults that are slowly creeping without building a lot of stress and resulting big earthquakes. But unfortunately for us, these yellow segments are something we call it the locked sessions, which they do build up a lot of stress, which doesn't move for 100 years or more, but suddenly release their motion in abrupt ruptures. So there's one in the north near the San Francisco, and that's responsible for 1906 San Francisco earthquake. And there's another one here in Southern California which is responsible for the 1857 Fort Tajon earthquake. This Fort Tajon earthquake is actually the last big one in Southern California on the San Andreas Fault. It was in January the 9th, 1857. The modern day estimate magnitude is about 7.9. There's only 2 people casualties at the time due to sparse populations. But we still don't know a lot about the events. For example, we are not so sure where it starts, but we do know from geological evidence, the offset between the 2 sides of the fault is about 9 meters in the northern part in Carrizo Plain, and it's about 6 meters in Palmdale. So what we are expecting is really pretty much a return of earthquake like this magnitude in the future. So here is a simulation of the ground motion resulting in a big one on the San Andreas Fault, where you will see the colors propagating, showing the amount of shaking intensity on different parts in Southern California. And the map has been rotated so that the San Andreas Fault is more or less horizontal. So the earthquake starts in the southern end of the fault near Salton Sea and is propagated northwest along the fault traces. So you can see most of the severe shaking is actually concentrated in about 10 miles away from the fault, except that when they get into the sedimentary basin in the metropolitan Los Angeles area and also the Ventura basins, where you can see the soft sediments in the basin really amplify the shaking. Okay, so that was an inherent challenge we face in LA. There is a lot of things for how we can better prepare for this earthquake or how to mitigate these seismic disasters. Now, the first thing we want to do is to actually avoid constructing the buildings on the active faults, right? So otherwise, no matter how strong the building is, if the 2 sides of the fault is going to tear the building apart, nothing can sustain. Actually, federal laws, state and federal laws forbid constructing of these buildings near active faults. So these areas should be zoned as parks, and ideally people should not live in 5 miles within the active faults. That's not always possible within the LA basin, although. There are other things we can do to better prepare these earthquakes. For example, we can reinforce or retrofit the existing the buildings. For example, this is one of the UCLA buildings, and we did put in these metallic bracing to reinforce the building to sustain the shear motions during earthquake. Another thing that people should be really careful is this tuck under parking in many of the apartments that we see in LA. So these soft storage parking often have only a few pillars to sustain the weights of the buildings above. So if the earthquake happens, it's really easy to collapse, and you probably lose your house as well as your cars in these situations. There's things we can also do to mitigate interior hazard inside of the house. Some easy things everyone can do at home. For example, you probably don't want to crowd your bedroom with a lot of heavy furniture, right? Or at least at a minimum, you should anchor these heavy furniture to the wall. Kitchen can be places with amazing mass, right? You have lots of breaking stuff, glasswares, and also there are water, gas, and heavy appliances. One easy thing we could do is to put latches or hooks in these kitchen cabinets, which really works great to prevent this falling off of the furniture. And another thing we could do is to, from the government point of view, is to issue earthquake early warning. And actually, California becomes the first state in the country to have a publicly available earthquake early warning system. The idea is if you have sensors closer to the active faults, they will be able to sense the big earthquake first and issue warnings to the metropolitan areas. And depends on how far you are, you get 10 to maybe up to 1.5 minutes warnings. And these warnings, when you do hear these warnings, when you're using these cell phones, which is delivered early warnings through the MyShake app, what you should do is to do drop, cover, and hold on, right? So this is the protocol. You should always drop down and slowly crawl under a shelter, like a table or maybe under the bed if the bed is high. And you should hold the legs of the table with one hand and cover your head with your other hand, right? And stay there until the shaking is stopped. So after the earthquake, we should always care about the injured people and try to meet your loved ones in some places which are previously agreed on, just in case all the communications was cut off. Another thing you should do is to go out and immediately check the lifelines like gas, electric lines, and water, and probably just close them. Right. I think that's all the time I have for today. Thank you for listening, and I'll be happy to answer some of the questions toward the end of this webinar.
Thank you very much, Ling-Seng. Thank you. I'm happy that you and your students are doing work to understand earthquakes better. And thank you for reminding us of the things that we can do to ameliorate the situation. So thank you so much.
Thank you.
Okay, yeah. So now we'll shift from our focus from what is beneath our feet to which is much further above in space. Professor of Space Physics within the Department of Atmospheric and Oceanic Sciences, Jacob Bernick, will share how space weather may affect both our way of life on Earth and how our explorations beyond these planets and our explorations beyond these planets. So Jacob, please take it away.
Okay, thank you very much, Miguel. So today I'm going to talk about space weather, and I called it When the Local Space Neighborhood Comes a-Knockin', when space meets us here on Earth. And what does that look like? I hope to give you a little bit of a flavor of that today. So I thought I'd open my talk with this very iconic photo. This is called the Pale Blue Dot. It was taken on Valentine's Day, February 14th, 1990. This was done by a very famous spacecraft called Voyager 1, just as it was leaving the solar system at about 40 astronomical units. That's about 40 times the distance from the sun to the Earth. And it was done at the request of Carl Sagan, who said, let's just turn it around and take one last photo. They captured this photo, and it became quite iconic because here, this little mote of dust, this little speck right here, that's the Earth. Carl Sagan wrote a famous book on this in 1994, and I'd like to quote just a little bit from that book. He writes, "Look again at that dot, this dot right over here. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you have ever heard of, all the rulers and tyrants, all the civilizations. They live their lives here on this mote of dust suspended on a sunbeam." That's it. This is us. It's spaceship Earth, and on it, all of us together are traveling through space. We're all, in effect, space travelers, and we circle around the sun, our closest star, at a dizzying speed. Our textbooks tell us about 30 kilometers per second or thereabouts. And we enjoy the sun's light and heat, warmth. It's a life-sustaining energy that moves around the atmosphere and the oceans and the space above it. And if you look at the sun in visible light, with our naked eye, the sun looks sort of like a constant yellow glowing orb, a little bit boring, doesn't change very much. But if you peer just under the hood, if you look at wavelengths, at frequencies that are different from the visible light, at wavelengths that are shorter, representing more energetic photons, hotter temperatures on the sun, you see that our nearest star is anything but boring. In fact, it can be dynamic and quite temperamental. Here I'm playing you a video shot in X-rays. So these are much shorter wavelengths than visible light. And you can see that the sun is no longer uniform. In fact, it's quite patchy. It has areas of brightness, areas of hot, areas of cool. And occasionally what you see is this immense cloud of gas. This is called a coronal mass ejection. It has roughly 1 trillion kilograms of charged or ionized gas called plasma, which is emitted in all directions outwards from the sun. Now, occasionally, I'm going to play this for you again as I speak over it. Occasionally, this coronal mass ejection is aimed directly at the Earth. And as it flies and impinges onto the Earth's magnetic field, what you see is that the magnetic field inside this coronal mass ejection strips off some of the Earth's magnetic field. It drags it backwards towards the tail of the Earth, reconnects in the tail, and this plasma from the solar wind becomes, or from the coronal mass ejection, hurtles back towards the Earth, and it creates these majestic auroras. So let me move on. Let's make this a bit quieter. And what I'm doing here is I thought I'd play you a little animation. So this is from the International Space Station. Look at the bottom left, please. And what you see is the International Space Station is at what we call low Earth orbit. It orbits around the entire Earth in something like 1.5 hours. And what is very common to see are these aurora borealis and aurora australis, these kind of green auroral spectacles of light, similar to what you see behind me in my background here. From the International Space Station, this is it's beautiful, it's majestic, it's very common. This occurs pretty much at every orbit at some low level, and occasionally it breaks out into these majestic curtains of light. You see greens, characteristically reds, a little bit of purples, a little bit of blues, usually in these undulating curtains that straddle across the entire subauroral region. So that's a beautiful, majestic display of nature. It's been written about for thousands of years, ever since people learn how to write or record information. But there's another side to these sorts of space events or space weather events. And this is what I'm summarizing in the right panel over here. Now, it's a very busy panel, so don't worry about reading the whole thing. I'll just summarize a couple of key points. Our technology, mankind's or humankind's technology is getting larger, bigger spatially, more sensitive. We're venturing out further into space, and we're exposing ourselves to more and more of our local space environment. For example, electrical power grids sometimes span entire continents, and so they can be susceptible to overhead million ampere currents that flow at about 100 kilometers or thereabouts. They can induce large currents and actually fry entire transformers. This happened in a famous event in Canada in 1989. We can have satellites that fly overhead and energetic particles that kind of charge up the surface. They can cause discharges. They can damage solar panels. They can even burrow through the skin and create phantom commands that tell the spacecraft all sorts of wild and wacky things to do. They're unanticipated. Astronaut safety is affected. GPS, your positioning can be affected. And a special problem if you are riding in an autonomous car or plane. But what is quite interesting, I thought I'd just stay on this for a second, is what we call atmospheric drag. I'll talk about why this is important in just a minute. But if you can imagine all these charged particles and all this energy kind of getting dumped into the Earth's upper atmosphere, particularly in this region called the thermosphere, which consists of the upper reaches of the, oh gosh, sorry, my computer decided to do something funny. The upper reaches of the neutral atmosphere, It's a region where the upper regions of the neutral atmosphere meet the charged ionized regions of space, right? They kind of interact together. And so all these energetic charged particles that impinge onto the Earth's atmosphere can actually heat it. They raise its temperature and they expand it. The atmosphere actually expands. And why is this a problem? It's a problem because it presents an additional amount of drag to low Earth orbiting spacecraft. Now, in 1978, there was an engineer called Donald Kessler, who worked in NASA, and he came up with this scenario where he said, if you populate a space environment sufficiently, for example, low Earth orbit with spacecraft, you increase the probability that two of these spacecraft will collide with each other. Right, that stands to reason. The more objects you have, the higher is the probability that any two of them will collide. But here's what happens next. If you have a collision, these spacecrafts will shatter. They will fragment into hundreds of different fragments, which increases the number of objects in this orbit even further. That increases the probability of collisions dramatically. And so now you're far more likely to collide with the next object, and the next object again would shatter into hundreds of fragments. And so very quickly you have this catastrophic cascade, and you populate the entire orbit with all these shards. And in fact, this is a catastrophe that could bring down the entire orbit's contents. So this was a scenario, it's called the Kessler syndrome, described in 1978. But let me tell you a little bit about what's happening right now. Perhaps some of you didn't know about this, but we are in a space commerce revolution right now. The number of operational satellites in orbit right now numbers slightly under 3,000 by many estimates. But what's happening over the next few years is that companies are going to populate low Earth orbit and other orbits dramatically. For example, SpaceX here is planning the launch of something like 30,000 more satellites in the next few years. That's just one company alone, right? A factor of 10 greater than what we have right now. Over the next 10 years, some estimates are that we will have 57,000 satellites or objects that are all predominantly going to be in this low Earth orbit. See, every dot here is a satellite, and here's the schedule, and here are the different companies that we know of currently are planning to launch multi-thousand spacecraft clusters. So over the next few years, we will be more exposed than ever before, especially to this phenomenon that affects satellites, right? Atmospheric drag. I mentioned that we're in a space revolution, and I think this is exactly right. We're undergoing what we call the space commerce revolution, where now it's not just about science or communications alone, but private companies are storming into this new and emerging market. The key to this is technologies that allow low-cost access into space. And so here I'm just mentioning a few things. Amazon Web Services launched a space accelerator program. This is just a few days ago, right? March 30th, 2021. Japanese budget for space activities is at a record high. The space industry here in the United States continues to grow. And here again, the Chinese private space industry is surging. In fact, Southern California happens to be a hub of aerospace research in the United States, and UCLA is in the lucky position that we are a long-time space science leader. So we find ourselves in a wonderful position. You see many companies, public companies, are facing hiring challenges, and we at UCLA are responding with hiring more faculty, boosting up our educational program. We're fortunate enough at UCLA to be awarded an aerospace accelerator program with a Starburst accelerator to kind of take ideas from concept and develop them into startups in the shortest amount of time. So this is what's happening right now in the world of space, in the world of space weather. What am I doing? What are we doing in my research group? Well, we think that one of the most interesting and promising avenues for research is the combination of space weather and machine learning. And the basis for this is this picture on the right-hand side here. This is what we call the Heliophysics System Observatory. Back in 1958, this consisted of one single satellite, right? The very first satellite that was launched, the very first rocket. And now we have hundreds of these satellites populating every corner of the space environment, taking high quality scientific measurements. You can see in this graph that the amount of data that we currently have in our data repositories is growing at a very fast pace, much faster than what we call Moore's law, which is a doubling every 18 months. That would give us something like a factor of 16 increase over the past 6 years. And the reality is we have something like 10,000-fold increase. So our data is exploding. It's tremendous. We at our group are using all this data or subsets of this data together with artificial intelligence to reconstruct whole environments. And what I'm showing on the right here is that when we simulate our data-driven machine learning enabled environments, they perform almost as well as the observations themselves. This is a combination of physics-based modeling together with artificial intelligence-based models. This is my last slide, but I wanted to say, what is the final frontier, if you pardon the pun? There are a lot of things to be excited about. In addition to these vast quantities of data that are coming down the pipeline, we have a range of algorithms that are exciting, and they promise to do things that we were never able to do in the past. For example, here's a plot that I'm showing from a paper by Rudy et al., and he's showing a simulation using the well-known fluid Navier-Stokes equations. And just by probing this and taking little bits of data out at various points, an algorithm is able to tell you what are the equations that created this data field. Imagine that. One day it might be possible to send a fleet of probes to some distant region of the solar system and have it not only take data autonomously, but write down the equations that describe that neighborhood. What is the physics like in this part of the universe? We also have ultra-fast equation solvers. We have real-time environmental reconstruction, but unlike the ones that I showed in my previous slide, there are algorithms that are now physics aware. They can reconstruct a data set being aware of what the driving physics are in the background, and many more exciting discoveries. So let me stop right there and hand you back to Miguel.
Well, thank you very much, Jacob. That is really fascinating. Well, now we have Tina Troide, Professor of Marine Geomicrobiology within Earth, Planetary, and Space Sciences, who will speak with us about the ocean. Tina's talk will explore why we should care about oxygen declines in the ocean. So Tina, please.
Yeah, thank you very much, Miguel. I just got my little laser pointer here. So welcome everyone this afternoon, and I'm going to take you to the ocean and talk about why is the ocean losing oxygen, and why are there areas in the ocean in the first place where there's very little oxygen. So I'm a marine geomicrobiologist, so I study very tiny organisms in the ocean, and I always like to say that I go from the tiny organisms to the big oceans and understand their effect on the oceans, but also vice versa. I try to understand how changes in the ocean will affect the processes that little tiny microbes do. And for my research, I frequently have to go at sea on research vessels to actually get our samples to study the ocean and the microbes. So oxygen minimum zones, and I'm going to call them OMZs in the following. So these are areas in the ocean where there's very little oxygen. But why is that so? So originally, it's a very natural process. So what's happening is, if we take this could be here the example of the California coast. And there are, particularly at the west coast of the continent, there are wind directions that when they blow parallel to the coast, they are, there is a direction of the water movement away from the coast, which has to do with the Coriolis effect, which comes from how our Earth spins. And because these winds ultimately lead to a transport of water away on the surface of ocean, this water needs to be replaced. So it gets replaced by water from the deep ocean that comes up to the surface. So if you ever wondered why in the middle of the summer here, it's the water is still cold, that's because of that, because we get this very deep cold water brought to the surface here. And this water also brings nutrients because it's very old water. It has been going through a lot of recycling. And these nutrients, algae loves. So algae, they grow immensely, make big biomasses. That's why we have, we have a lot of organisms here in the ocean that feed ultimately also off of these algae. And so when we have these blooms, they die off also. I mean, every life ends at some point. And so this organic matter, how we call it, is then sinking through the water deeper through the ocean. And while it's sinking down, it's degraded by microorganisms and they consume oxygen. And so you can get these, what is red here, you can get these zones close to the coast, but also off the coast where you have very little oxygen. And again, this is a natural process, originally nothing to worry about. And here is a map showing you where we find these oxygen minimum zones. Everything black here you see, and as I said, most of them are on the west coast of the continent. There's also one developing here and has to do with the main wind direction. We see also some here in the Arabian Sea and off India that has to do with the monsoon winds. So again, naturally occurring oxygen minimum zones. However, there have been studies over the past 50 or so years that show that oxygen is declining in all the world oceans, and it's declining in concentration, but also these oxygen minimum zones, they're spreading around, so they're expanding. And so what you see here, these are different regions that you could also see just on the previous map. And this here is oxygen concentration in micromole. But what is important to notice here is where you see these darker bluish colors is where we see very little oxygen. And you see that this is over time. You see that in different oceans, the extensions on this here is water depth on the left side. So there was more over depth, more oxygen loss, and also in the intensity. So it gets darker and darker in some places. And then we have also observed that it's spreading laterally. So what was like a smaller area from bird eye view now becomes a larger area. Why is that? So why do we have this expansion of the oxygen minimum zones? There are several reasons for that, and they're caused by human activity. So one effect is the global warming. So we get warmer temperatures in the atmosphere, and they warm also up the upper ocean temperatures here. And then you have this warm blanket of water on top that is very light. And that prevents actually ventilation so that oxygen can be brought deeper into the ocean by wind. And the other thing that's happening just physically is that if you have warmer water temperatures, less oxygen can dissolve in water. It's just a physical process. The other thing that's happening is that we bring in more nutrients to the ocean through agriculture that brings in the nutrients that we put on the fields that comes in with rivers, and that produces more algae blooms. And that means more organic matter is getting degraded and draws even more oxygen out of the water. Okay, so what does happen now when the oxygen disappears? So here is a lot of chemistry to see. So for those of you who are into chemistry, you can take a look at this left-hand side, but I want to put your attention here to the left side. And that is when oxygen is gone, then microbes can do something very special. They can breathe other things than oxygen. Like we depend on oxygen, but microbes can switch to other things. They can breathe nitrate, they can even breathe metals like manganese and iron, they can breathe sulfate, and they can breathe CO2 and produce methane from it. And so once one of the other is gone, then they jump just to the next. And why is that interesting now? So one thing is that if they jump to breathe nitrate, this process has a side effect. It produces a gas called nitrous oxide, N2O. And that's a greenhouse gas that's about 300 times worse than CO2. Another thing here is when they jump to sulfate reduction salt. A sulfate is the salt of sulfuric acid, very abundant in seawater. When they breathe that one, they produce hydrogen sulfide, which is a toxic gas that kills fish and other animals. And if they jump to breathing CO2, they produce methane, and methane is also a very strong greenhouse gas, about 25 times worse than CO2. And if we now look what happens at the seafloor, it's happening everywhere in the water and in the seafloor, but at the seafloor, it becomes very visual what's happening if you take out more and more oxygen. So basically, these are photographs of sediments at different oxygen levels, so oxygen rich to oxygen poor. And here you see there are still a lot of animals living, digging through the sediment, and the sediment looks like brownish. That means there's a lot of oxidized iron in there. And but that where only microbes live. Okay, so why do we as humans care about the spreading of the oxygen minimum zones? So one thing is very simple. If there's no oxygen, there's no fish, there's no seafood. So by expanding these oxygen minimum zones, we are removing the environment where fish can live and shellfish, all the things we eat. And a lot of our populations depend on seafood. So that's not good if it spreads. Also, sulfide production kills fish, and not only fish, there has been like off Namibia, there was sometimes so much sulfide produced that the lobsters were literally walking out of the water to escape the sulfide. And then, of course, we have this greenhouse gas production that I introduced, and they create a positive feedback. So they create even more warming, which will lead to more expansion of oxygen minimum zones. Okay, so I don't have enough time to go a lot into detail of the research particular that I'm doing, but I want to give you a very quick wrap up. So I'm currently working in two areas right off our coastlines here in the Santa Barbara Basin and in the Santa Monica Basin. And here just off our coast, it's a very special bathymetry, so the topography of the seafloor. And it has to do with tectonics that Lingsen Meng just explained to you, how like plates are rubbing against each other here. And that deforms the seafloor and makes all these basins. And we call this the California borderland. And you can imagine, for example, this here to be the Santa Monica Basin, and this here would be Catalina Island. And you create these bathtubs. And we have this upwelling of water here due to the wind direction that brings the nutrient-rich water to the surface. But at the same time, we have this bathtub now where when the material is getting degraded and oxygen is being removed, there is not a very good ventilation because of this bathtub effect. And so we are trying to understand now what's happening in these strong oxygen minimum zones that we have in the Santa Monica and Santa Barbara Basin. And so one project that just came to an end and we are wrapping up the data is a project that was funded by NOAA and Sea Grant, and that is also in collaboration with the Southern California Marine Institute. And we used the Yellowfin, the ship, to go out just off Malibu, basically, and took sediment cores here. And we tried to understand what has happened with the oxygen minimum over the past 40 years, which was when the last study was done. And so we took sediment cores, and from the sediments, you can tell, like, if you see a sediment like this, it's very bright, it's very bioturbated, a lot of animals living in there. Whereas this one here has these laminations, so it's just layer after layer after layer, because no animals live there that can really like dig through the sediment. And that's an indication for us, and together with a lot of geochemical studies, whether the oxygen, like how much has the oxygen been, expanding. And so we did corings here in the basin and compared that to old studies. And here you see actually oxygen concentration in the Santa Monica Basin, and you see that below like 400-meter water depth, which is about 1,200 feet, is where oxygen gets really, really low, where you have almost, no animals living anymore. And the good news is from this study, actually, what we found is that we couldn't find an expansion of the oxygen minimum zone over the past 40 years. We might even see a little decline, and that was based on the sediment cores. And that was a collaboration with USC, so Will Barrelson's group there, who did a lot of these analysis of the lamination. And so we don't know what the reason is. Maybe it's because like the sewage treatment has been improving and there are less nutrients coming into the basin, but it was a surprise to us. The other study we are currently doing is a project funded by the National Science Foundation, where we go out with big research vessels to the Santa Barbara Basin, and we try to understand the feedback from the seafloor in response to oxygen deficiency. And what you see here is this white, what looks like mold is actually a giant sulfur bacteria mat, and the Santa Barbara Basin has the largest sulfur bacteria mat ever discovered so far on our planet. And we try to understand how this is like relating to oxygen decline. And we go out with large instruments, with robots, and we deploy like chambers that's like an upside down bucket, so to say, on the seafloor to measure certain things. And so here's just to give you a very quick insight. So what we found in these chambers, we found that the sulfur bacteria, they are releasing a lot of ammonium from the seafloor that has to do with the way they do their reactions. So they couple the hydrogen sulfide oxidation with nitrate, and then they produce this ammonium. And now the next step is that we also try to understand what is the impact back to the surface ocean, because ammonium is a very strong nutrient and could fertilize more algae blooms. So that's one thing we are still working on. And so I leave it with that, and hope you have questions later from me. Thank you very much.
Thank you very much, Tina. Thank you for making us aware of the importance of oxygen in the ocean. So our final presenter will focus on a topic that has been front and center in recent years, which is climate change. Alex Hall, director of the Center of Climate Science and AOS professor, will share how UCLA is leading the way by actively partnering with agencies to address global issues on a local level. Alex, please.
Great, thank you so much, Miguel. I will share my screen here. It's really a pleasure to be here this afternoon and to be in the company of such amazing colleagues that we have at UCLA. I wanted to talk about work that I've been doing in conjunction with my center at UCLA, the Center for Climate Science, on projecting regional climate change. And I wanted to start out with just a little bit of an overview of the science that underpins a lot of this work. So as many of you may know, particularly if you were AOS graduates, the equations that govern atmospheric and oceanic motions, they're very complex and they're nonlinear. And they can't be solved with traditional methods of calculus. So here's an example of one of the key equations for the atmosphere-ocean system. This is the equation that governs the motion of air and water on a rotating Earth. And I'm not going to obviously go through this equation in too much detail, except to note that it is very complicated. It has terms multiplying themselves. And so it is very, very, what we could say, nonlinear. And the implications of this are that global climate models, the tools that we have to understand the climate system, they have to be employed. And so what are these models? Well, essentially they are tools to do brute force arithmetic to solve these atmospheric and oceanic equations. And so here is just a picture that's showing you the grid that might be used for such a model. You can see, I think, hopefully a little bit of the topography of or the geography of the planet, the coastlines of Southeast Asia and India are particularly visible in this image. And this snapshot is just showing you temperature. So the colors here are corresponding temperature, and the arrows are winds in this model. So at every single box here, the model would be producing a single piece of information about the conditions at that point, whether they be temperature, humidity, solar radiation, infrared radiation, or latent and sensible heat fluxes. And so these are the models that we use to study the impact of increasing greenhouse gases on climate, otherwise known as climate change. And these models developed in the 70s and 80s, the last third of the 20th century, basically. And they've been in use ever since to study climate change. And the resolution of these models has been increasing, which is really great. At the same time, the resolution increases have not been nearly enough to study climate change in areas with complex topography and coastlines. So we are a prime example of a region with complex topography and coastlines. A lot of that is the result of some of the processes in the interior of the Earth that were discussed earlier in this presentation today. But for the purposes of climate, the topography and coastlines create a lot of complexity. And so here is a blow up of Southern California. Hopefully you can recognize some places and features here that are familiar, but we have the San Gabriel Mountains, the Santa Monica Mountains here that separate downtown and the LA basin from the San Fernando Valley. And then we have the southern part of the Sierra Nevada here at the very top. Now I'm going to overlay on this a typical grid for a current generation of global climate models with a resolution of maybe 100 kilometers or so. And I think you can see that if you focus on one of these grid boxes, we could, for example, look at the one that encompasses Palmdale. You can see that that spans a region that has a lot of variation in climate. So in the southern part, where Pasadena is found, you have one type of climate, then you go up into the San Gabriel Mountains, and that's very different. And of course, there are huge variations within the San Gabriels. And then you get into Palmdale in the Antelope Valley, and that is a totally different area as well. So this grid box for a global model is really insufficient for describing the climate in this region, especially the climatic variations. And of course, if we're talking about climate change and we're talking about trying to adapt to a changing climate, we need information at the landscape scale, at the neighborhood scale. And so that's why at UCLA, I've been pushing really hard to do regional climate modeling. So what is regional climate modeling? Well, this is something that we call downscaling, and that's because we're taking information from a global climate model and we are imposing it on a different type of model, which we call a regional model. And on the right is an illustration of the setup of a regional climate model. This is a setup that we're actually working with right now to produce climate change information for the Western US and for California. And so what happens is we take the data from the global model, and at the boundaries of the regional model, we impose the evolution of climate from the global model. And then we have much higher resolution nests within this setup. So you can see over the Western US, we have a resolution of 9 kilometers. And then there are higher resolution grids over, for example, California, that has a resolution of 3 kilometers. And what we do is we solve the same equations of the atmosphere and the land surface and the ocean in some cases as well as the global model solved, except that we're solving those equations on a much higher resolution grid. And it's tractable because we're doing it over a limited area. And so this is work that we've been doing a lot of recently to try to understand the impacts of climate change on places like California. So here's a blow up of the 3-kilometer resolution grid that I mentioned that covers the state of California. So this is almost a 2-mile resolution grid. And with that resolution, I think you can see that we would get a lot of the main topographic features of the state of California. And we'll be imposing the output from many global climate models on this regional model setup to simulate climate and climate change in this region, corresponding to different realizations of the region's climate future. So every global model is producing different outcomes, different responses to the increases in greenhouse gases. And so we have to downscale each one of those variations in the future to map out the uncertainty associated with climate change. This is a huge effort. It requires a massive amount of computational resources. We're using a machine that is operated by the National Centers for Atmospheric Research. And we're using about 30 million core hours on this machine to do these simulations. And that's something like 4 times 10 to the 21 arithmetic operations. So if every one of those operations was represented by a grain of sand, how much sand would that be, you might ask? Well, if there are 1.7 billion grains of sand in a cubic foot of sand, then those 4 times 10 to the 21 grains is about 16 cubic miles of sand. So it's a huge number of computations and a massive effort that's required to produce this climate change information for the state of California. So what's an example of the type of information that we might produce from a simulation like this? Well, we've undertaken previous downscaling efforts, and this is a plot that shows the outcome from one of those efforts. This is a map of snow loss in California's Sierra Nevada. And California is kind of tilted on the side here. So you can see that north is kind of pointing towards the upper left of the screen. And so California is tilted on its side. You can see the Bay Area down here in the lower left. And you can see the boundary between California and Nevada in the upper part of the plot. And then we have the main features of the Sierra Nevada from Lake Tahoe, Yosemite National Park, Mono Lake, the Mammoth Lakes, Sequoia and Kings Canyon National Parks, and the Owens Lake in the southern part. And the colors here are showing the percent loss of snow on April 1st, the end of the wet season in California. And the darker brown colors are showing almost a total loss of snow cover. The lighter colors are showing that the snow is not lost at all. You can see that in most of the Sierra Nevada, the snow is lost entirely, especially in the mid to low elevations. Whereas in the higher elevations, say where Mount Whitney is located, much of the snow is preserved. So a really massive change in the amount of snow that is in the Sierra Nevada, with huge implications for changes in water resources, because as many of you may know, the snow in the Sierra Nevada is a huge natural reservoir of water. When the snow accumulates in the wintertime, that stores up water for the summertime when it's most needed. And the regular melt of snow from the snowpack in the summertime creates a reliable water source for agriculture, especially in the Sierra, in the Central Valley, but also for urban water users. So this change in snow loss is really important for California's water resources. So this is an example of the type of work that we will be doing with these simulations that we're producing. One of the most important areas that we'll be focusing on coming up in our future work is to look at the impact of climate change on wildfire in California. We've already seen a dramatic increase in wildfire in the state that is due, at least in part, to the changes in climate that we've already experienced. this has been associated with tragic loss of life and property. It has resulted in the shutdown of the electric grid in urban parts of the state and elsewhere, which has inconvenienced many people. It has led to really huge deteriorations in air quality. I'm sure many of you remember last fall, late summer and early fall, we had really dramatic deterioration in air quality that caused a lot of problems for public health and impacted especially disadvantaged communities. And then finally, we know that wildfire is also very costly, just in terms of fighting it and the damages that are associated with it. About $20 billion was the bill for last season's wildfires. So huge implications of a changing climate. If the climate continues to worsen wildfire, which we believe it will. And so that's one thing that we are focused on studying. The experiments that we're doing are designed to produce information about changes in climate extremes, such as droughts and floods, in addition to the warming effects that could lead to losses of snow cover, for example. And in the case of the changes in fire risk, we're going to be using the data to understand how climate change will lead to a buildup of vegetation in forests and in chaparral through wetter and more frequent wet years. And at the same time, we know that climate change will bring warmer temperatures during the summer, and that will dry out vegetation more. And that could in turn lead to a more dangerous fire weather during the fire season. And that's the cycle that we believe has played a part in the recent increase in fire. And that is likely to continue as these trends accelerate. So we'll be quantifying where fire risk will increase in California and examine why. So the work we do, and these pictures are the people who are part of the team here at UCLA doing all of this really incredible work. Our goal is to do climate change simulations and produce climate change information that will help to design strategies to build a more harmonious and sustainable relationship with California's ecosystems. Of course, fire is a critical part of ecosystems in California. And the data also has a very direct public impact in the sense that it is publicly available and will be part of the climate change data portal that is being produced by the state of California within the next couple of years. So I hope this gives you a flavor of the type of work we are doing. With that, I will wrap up and return the floor to Miguel. Thanks.
Great, thank you very much. Thank you, Alex. So, this has been incredibly interesting presentation. So I'm going to ask Jacob, Tina, and Lindsay to join us to show their videos. This has been really exciting and interesting and important, and we obviously ran out of time. So I think we will have to skip questions, but I'm sure, please correct me if I'm wrong, but I'm pretty sure that you will be more than happy to answer any questions that anyone in the audience will send to you directly. I think, I want to thank all of you. I think that you made incredible presentations of really interesting and important research. I also want to thank all of you who joined us today. So we have a good number of participants. Many of you are alumni of these two departments. I know there are many of you are friends of UCLA and people who are curious about science. So I will remind you that these webinars are posted on YouTube. So if you want to check it out again and come up with another set of questions, you're more than welcome to do that. And we definitely want you to keep coming back. So I think our faculty are eager to share the wonderful work that they actually do with their students. They're not only incredible scientists, but they're amazing teachers, and UCLA is very, very lucky to have them in our ranks. So thank you, everybody. We'll see you next time. And until then, please be safe. And bye-bye.
Thank you.
Thank you for coming.